Namaste and welcome to this lecture on mathematical foundations for machine learning. We've been in the last couple of classes we've been looking at linear transformations, and we were actually trying to study what a linear transformation could do. Basically we said that it is going to be a map from one vector space to another vector space, preserving vector addition and scalar multiplication, and we also said that any line passing through the origin is going to get mapped to another line passing through the origin by a linear map. So, the what do you call the properties of vector addition and scalar multiplication is preserved. And in the process we were also looking at what are the subspaces associated with the linear transformations. We said that okay, the set of vectors in the vector space V, which is going to get mapped to the 0 vector by the linear transformation say T, we call that as the kernel, and the set of vector space, the set of vectors in the vector space W which actually have a pre-image in V, we call that as the range of the transformation T. And in the process when we went, we also had this question like every linear transformation is going to take one vector and then map it to some other vector, but we had a question where it says, do we have transformations or do we have vectors for a particular transformation where in which the transformation does not change the direction of the vector. For example, I have a vector space V, it is a map from let us say V to V. So what is it that we had? So let us do this. We had this, let T be a linear map from V to V, from vector space V to the same vector space V. So what are we going to say? I am going to say T is that such that it is going to map vector in V to another vector in V, right. For example, let us try to very specifically say I am going to look at say let T map from let us say R2 to R2. So it is a linear transformation which is going to map a vector from R2 to R2. And that what does that mean? I am going to get let us say x is a vector, I mean let us say u is a vector here in R2, let u be equal to u1 u2 and let v be another vector in R2 such that it has these two components, let us say v1 v2. Now let us say that okay, the transformation T is going to act upon this vector u1, I mean the vector u whose components are u1 u2, and it is going to put it is going to give you another vector which is let us say v1 v2. Now what does that mean? It could actually mean something like this. I have let us say I have this, I have this, say for example I have let us say x1 and x2, I have let us say x1 and x2 here. So this is going to be my domain for the transformation T, and this is going to be my codomain of T. Now assume that I have this vector which is say u1 u2. Now what is the transformation going to do? The transformation is going to act on this, right, it is going to act on this, and then let me say that I am going to get a completely different vector here. Let us say I have a vector which is this basically V, which is v1 v2, right. Essentially you can capture all these things in a single view graph. You have this, say I have x1 x2. Now what am I going to say? I have this vector let us say which is u with components u1 and u2, and I have the linear map which is going to act on this. So let us say I am going to have this is the transformation acting on this, and what am I going to get? I am going to get a completely different vector which is here, or probably let us take this. So, this is the vector that I have, which is V1 V2, right. What does the transformation do? The transformation basically takes this vector u and then results in a vector v. Now, there is something interesting that happens here, the direction of u and the direction of v are completely different, right. So, u and v are in different directions. Right, they are in two different directions. Now, the question we asked even in the last lecture, we stopped with this question. We said, like, can we have consider a transformation T, whenever I say transformation, it is a linear transformation. Consider a linear transformation T such that you have, say, some vector, say u1, the transformation acts on this vector, say u is equal to u1 u2, it is going to result in a vector which is going to be the scalar multiple of this vector u1 u2, which is nothing but k u1 and k u2, right. What does that mean now? That is pretty interesting. Say, suppose I have this, let us say x1 axis and I have, let us say, x2 axis, and let me tell you that, look, this is the u vector that I have, this is u is equal to u1 u2. Now, what I am going to say is, can I have vectors u, say a vector u for the transformation, linear transformation T, such that when the transformation, when the vector u is going to get transformed by this T, the resultant is going to be something along this, the result is going to be, let us say, either this, or the result is going to be, let us say, this in the same direction. Right. So, this is going to be, let us say, k times u1 u2. So, what am I going to say? I am going to say that, look, this vector that I had u, this vector got transformed by, let us say, this got transformed by L, the transformation T of u1 u2 is equal to k times u1 u2. Now, if k is greater than 1, then you say that, okay, the vectors got stretched, and k is less than 1, you say that the vectors got compressed. So, this is what we have. That means the input and the output directions are going to remain the same essentially. So, what does this imply? This simply means, this means the direction of the output, the direction of the output vector of the transformation of T is the same as the input direction. Input vector direction. For example, you have a bowler in a cricket match who is trying to bowl the ball to the batsman, and the batsman does a straight drive. That means the input direction and the output directions are the same, right. That means this input vector, whatever I had given, suppose if I take the input vector to be u. So, let u be the vector, basically the input vector to T, right. The output is, as I said, k times u. The result of the transformation is the result of the transformation T is scalar multiple of u, and now what does this actually imply? This simply means the following. This implies that the vector u is invariant, the vector u is invariant to the linear transformation. What does that mean? That means no direction change or reorientation happens, no direction change or no reorientation, right. This vector u, if it is not going to undergo a direction change by the effect of the transformation, by the transformation T, then the vector u is called the invariant vector, and we give a name for this. This is called the eigenvector for the transformation T. So we are going to say that if T of u is equal to k times u, where T is a linear transformation, where T is a linear transformation and k is a scalar, and k is a scalar, we say that we say or we call the vector u as the eigenvector, as the eigenvector of T, and the scalar k is called the eigenvalue. The scalar k is called the eigenvalue. The scalar k is called the eigenvalue. Now let us consider any transformation, linear transformation T. Let us see if we have at least one vector which is going to remain invariant upon the application of T, right. So for any linear transformation T, or any, let us say, linear transformation T from Rn to Rn, from let us say Rn to Rn. That means this is actually a linear map where the domain space and the codomain space are the same. So you are going to have linear transformation T from Rn to Rn. The question is, do we have at least one vector which is going to remain invariant? By the property of linear transformation, we know that the 0 vector exists. The 0 vector is going to be unharmed by the transformation, because the transformation acting on the 0 vector is going to give me 0 vector itself, right. So we see that the transformation on the 0 vector is going to give me the 0 vector itself. But there is a problem here. What is the problem? 0 vector does not have a direction, it is just a point there, it is just the origin, it does not have a direction. Therefore our hunt is basically for a non-zero vector for the transformation T, which is going to map from Rn to Rn such that the effect of the transformation is just to scale the vector. So we are going to look for non-zero vector. So the eigenvector, so let us also make the statement. So the eigenvector or the invariant direction is basically a non-zero vector. The eigenvector is a non-zero vector. right, because this 0 vector does not have a direction. So, there is no point in basically trying to transform this, because whenever you try to transform you are going to get to the 0 vector itself. So, what we have is, when we talk about eigenvectors, we are going to talk about non-zero vectors which get transformed to the same vector, basically a scaled version of this. So, the question is, how do we get such vectors? So, what is it, how do we get, or how do we identify or obtain the eigenvectors for a linear map, for a linear transformation T from Rn to Rn. See, basically we call this as a linear map or a linear operator which is going to map from Rn to Rn. If you say linear transformation, it could be two different spaces, say Rn to Rm, in which case we will not be able to talk about eigenvalues or eigenvectors. So, it is going to be mapping from Rn to Rn itself, right. That means the matrix that is going to be associated with this linear transformation is going to be a square matrix. So, it is going to take an n by n, the transformation T is going to take an n component vector and is going to give us an n component vector. Therefore, say that okay, we are going to have an n by n matrix, right. So, the transformation, the matrix associated with the linear transformation or the representation of the matrix representation of the transformation is going to be a square matrix, right. So, how do we identify or obtain these eigenvectors, right. So, what do we do with this? So, let us see what are we trying to find out, or how are we going to do this business, right. So, let us look at this. Suppose A is the matrix that, or let us say A is a matrix representation of the transformation T. A, let me make it n by n, is the matrix representation of T. Then T of x, T of u vector is equal to Ku can be expressed as matrix operation, can be expressed as Au is equal to Ku, right. It can be expressed as Au is equal to Ku. So, this is what we are trying to look at. Now, what does this mean? This simply means the following: I have Au is equal to Ku, where K is a scalar, where K is a scalar. So, what I do is I write this as Au. I want to get a matrix equivalent on the right hand side. So, I will write this as K times the identity matrix into U. So, what I have is Au is equal to K times Iu, where I is the identity matrix of order n by n, identity matrix of order n, right. So, I have Au is equal to K times Iu. So, which is nothing but A minus K times I into U is equal to the 0 vector that we have here, right. Now, if you remember your foundation course on linear algebra, you call this set of equations where Ax is equal to 0, you call that equation to be the homogeneous system of equations, right. You call this, so basically this is called the homogeneous system of equations. This is the homogeneous system of equation, and what are we looking for? We are looking for homogeneous system of equation. The solution that you have here in terms of U is going to be a non-zero solution, because we already know that if you have a homogeneous system of equations, x is equal to 0 is always a solution, right. Ax equal to 0 implies x is equal to 0 is always a solution. Therefore, what are we looking for? We are looking for a non-zero solution to the homogeneous system of equation A minus Ki times u is equal to 0. Now, since A minus Ki is a square matrix and you are looking for a non-zero solution to A minus Ki times u is equal to 0, the 0 vector, this essentially means that the matrix A minus Ki is a singular matrix, right. So, what do we do here? We write, okay, this implies we want to see if, or probably we would put it this way. Since u is a non-zero vector you are looking for, we are looking for as a solution to the homogeneous system of equations A minus Ki times u is equal to 0, we infer that the matrix A minus Ki is a singular matrix. This means, this implies the matrix A minus Ki is not invertible. Matrix A minus Ki is non-invertible. This implies determinant of A minus Ki is equal to 0, and there is a name for this expression, determinant of k minus ai is equal to 0. We are going to call this as the characteristic equation of the matrix A, or characteristic equation associated with the linear transformation T represented by the matrix A. So, we are going to say this is the characteristic equation of A. The best part is, if you solve this characteristic equation, the roots we get are precisely the scalars that we are looking for, right. The scalars that we are looking for as that will be the scalars which will multiply this vector u, right, or that is the amount by which the vector u gets scaled upon the action of the linear map T. Is that clear? So, what are we going to do? So, let us write this. So, we are going to say that the roots of the characteristic equation are precisely the scalars that are precisely the scalars that scale the vector u right upon the action of T on u. That means, in this case we are going to say the action of T upon u is captured in terms of the matrix operation A u, and what we say is we are trying to look for the non-zero vector here. Okay. So, the roots of this characteristic equation are precisely the eigenvalues of, so that is what we had written here. The scalars are basically called the eigenvalues. So, we are going to write the same thing. So, the roots of this equation are precisely the eigenvalues. So, these roots are called as these roots, or let us write this, the roots of the characteristic characteristic equation, the roots of the characteristic equation are the eigenvalues. Equations of A are called the eigenvalues. Of A. Is this clear? And once you get the value of, once you get the eigenvalues, you substitute for different k here, you will end up getting different vectors which get scaled. So, you basically get the eigenvalue and its corresponding eigenvector. So, those would be the invariant directions for a transformation. Say for example, let us look at this. We already had our example case where we had this example. Let us say here is a linear transformation which is going to operate on, let us say, vectors in R2, to give vectors in R2, and is defined by transformation on the vector xy is given by 2x plus y and x plus 2y. 2x plus y and x plus 2y is the transformation that I am going to have. Therefore, the matrix associated with this transformation T, M of T, is basically A, which is given by 2 1 1 2. Now, what are we looking for? We are basically looking for the characteristic equation, or we are basically looking for the vectors A u, which is equal to, let us say, k u. In the textbooks you will see this as A u is equal to lambda u. So, I can actually put that. So, instead of k u, let me change this to lambda u. Right, where lambda is a scalar. So, let us take this matrix. So, what we want? We want 2 1 1 2 1 2. So, the vector u is going to be a 2 component vector. It is going to give me lambda into u1 u2. Now, we will do the a minus lambda I business. So, we are going to get, which implies a minus lambda I times u is equal to the 0 vector, implies we have 2 1 1 2 minus lambda times the identity matrix. The whole thing into u is going to give me the 0 vector. So, essentially what we have is 2 minus lambda 1 1 2 minus lambda into u1 u2. This is the vector which is going to give me the 0 vector. Now, what is the characteristic equation of this? The characteristic equation of this is determinant of a minus lambda I is equal to 0. We know how to find the determinant of this matrix. The determinant is 2 minus lambda the whole square minus 1 is equal to 0. So, we have lambda squared minus 4 lambda plus 4 minus 1 is equal to 0, which implies we have lambda squared, we have lambda squared minus 3 lambda minus 4 lambda plus 3 is equal to 0, which implies if you you factorize this, you basically get lambda minus 3 into lambda minus 1 is equal to 0. So, what are the values of lambda? Lambda I am going to get it as 3 and lambda 1 is 3 and I am going to get the second root lambda 2 is equal to 1. Now what we want is we want to find out the eigen directions in this case. So let me take lambda 1 is equal to 3. This means I have 2 1 1 2. So I have AU is equal to 3U. So I want to find out what is this U vector. So I have U1 U2 is equal to 3 times U1 U2. So essentially what I have is 2 minus 3 1 1 2 minus 3 into U1 U2 is equal to 0 0. So I have minus 1 1 1 minus 1 U1 U2 is equal to 0, which implies you have the two equations, namely minus U1 plus U2 is equal to 0 and U1 minus U2 is equal to 0. This implies, okay, let me write this, minus U1 plus U2 is 0 and U1 minus U2 is equal to 0. From both the equations we see this U1 is equal to U2. Therefore, the vector U is such that U1 U2 is the vector U1 U2, wherein which we are going to say this is going to be equal to U1 U1. Let me write, since U1 U2 I have to parameterize this, I can't write it as U1 U1 because that's the solution that we are looking for. So we are going to say take this as, let us say, small t and small t. So the vector U is basically a scalar multiple of this vector 1 1. Therefore, we are going to say the eigenvector associated with lambda 1 is equal to 3 is t times 1 1. Basically I will take it as 1 1, and then what I do is I will say every scalar multiple of this eigenvector is also an eigenvector for the matrix 2 1 1 2, or for the linear transformation which is given by 2 U1 plus U2 and U1 plus 2 U2, right. So the eigenvector associated with this lambda 1 is equal to 3 is 1 1. Let us check if it actually happens. Now what does this mean? This implies I should actually do this. I have to check whether AU is equal to 3U. I do not know, I will have to calculate and then check. So what do I have? I have 2 1 1 2 and the vector is basically 1 1. So I have 2 plus 1 which is 3 and 1 plus 2 which is 3, which is 3 times 1 1. So essentially we see AU is equal to 3U. Therefore, U is equal to 1 1 is an eigenvector, or it is an invariant direction to the transformation which is 2 U1 plus U2, and which is going to act upon any vector, let us say x1 x2, to give you 2 x1 plus x2 and x1 plus x2 as the components of the resultant vector. Let us also check what is the eigenvector associated with lambda 2 is equal to 1. So lambda 2 is equal to 1. So again I have the same business. What is it that I am going to do? I am going to take AU is equal to lambda U, lambda 2U, right. So I have, or AB, let me take this as V because we have already taken U. So let me take this as AV is equal to lambda 2V. So I have 2 1 1 2 into U1 sorry V1 V2 is equal to 1 time V1 V2. So now I can take it as A minus lambda 2 times V is equal to 0 vector. We have this. So I have 2 minus 1 1 1 2 minus 1 into V1 V2 is equal to 0 0. So I have this where both the equations are basically, both the rows of the matrix are 1 1 1 1 into V1 V2 is equal to 0 0. This implies both the equations tell us that V1 plus V2 is equal to 0, implies V1 is equal to minus V2 or V2 is equal to minus V1. Therefore, the vector is basically V1 V2 is equal to, let me again take some parameter which is going to be S1 S minus S, where S is the parameter. So, I am going to take this as S and minus S. Therefore, the set of vectors I am going to have are S into 1 minus 1 for S some scalar, S arbitrary and real. There also we have t to be arbitrary and real. So, you can actually take any t value and that would essentially become the eigenvector. So, what does this mean? So, I have AV, I want to check what is AV. This is nothing but 2 1 1 2, V is nothing but 1 minus 1. So, what do we have? We have 2 minus 1 is 1, 1 minus 2 which is minus 1. So, which is 1 time 1 minus 1. Therefore, we have this implies AV is equal to lambda 2V. Therefore, we say that V is equal to 1 minus 1 is the eigenvector associated with lambda 2 is equal to 1. For this particular transformation, eigenvector associated with lambda 2 is equal to 1, right. Therefore, if you look at this linear transformation T, which was trying to map every vector, let us say x y to 2 x1 plus x2 and x1 plus 2 x2, this transformation is such that we have transformation on the vector 1 1 is going to give me 2 plus 1 1 plus 2, which is basically 3 3, which is essentially 3 times 1 1, and the transformation on the vector let us say 1 minus 1 is going to give me 2 minus 1 1 minus 2, which is basically 1 minus 1, which is the same as 1 time 1 minus 1. That means, for this particular transformation that we have here, linear transformation that we have here, the eigenvectors are 1 1 and 1 minus 1. That means, these two are the invariant directions. So, the invariant directions are the invariant direction for the above T are 1 1 and 1 minus 1. So, if you apply this transformation in these direction 1 1 and 1 minus 1, the result is just scaling of this vector, right. So, the eigenvalues and eigenvectors are very essential as far as our linear transformations are concerned and applications in machine learning are concerned. In fact, many other applications have a lot of importance attached to the eigen directions or the invariant directions. Now, let us check one more here and then let us make one more statement here, right. Okay. Now, if you look at this transformation represented by this matrix, let us say 2 1 1 2, and now what I am going to do is I am going to look at any vector which is going to be let us say a scalar multiple of 1 1, right. That means I am going to take t multiple of 1 1, that is going to be the vector itself is going to be t comma t. So, what am I going to get? I am going to get 2t plus t, which is 3t, and 1 plus 2t 1t plus 2t, which is 3t, which is again 3 times let us say t times this vector. Similarly, let me take this 2 1 1 2 into let us say s minus s. So, what am I going to get? I am going to get 2s minus s, which is s, 1 minus s minus 2s is equal to minus s, which is nothing but 1 time s minus s. You keep changing the values of s and t, you end up getting different vectors, but all these vectors are aligned. If you take tt, the vectors are all aligned along the line passing through the origin and the point 1 comma 1, and all the points you take this s comma minus s, this is nothing but the set of points in the direction of a line passing through the origin and through the point 1 comma minus 1. Now, what do we see here? If you look at 3 and 3 t t, if you look at this set of vectors, this is basically a line passing through the origin. This is basically a line passing through the origin. So, all those vectors lined along this line are going to be the eigenvectors for this, right, passing through the origin, and 1 time s minus s. This is also a line passing through the origin. Here we will write it as and 1 1 line passing through the origin, and 1 minus 1. From our knowledge of vector subspaces, we know that a linear line passing through the origin is basically a vector space, and therefore, for a linear transformation or for a linear map that we have something like this, which is 2x1 plus x2 x1 plus 2x2, we just not have one vector which is going to be the eigenvector, but every vector aligned along the direction of 1 1, that means scalar multiple of this 1 1 is going to be the eigen direction or the invariant direction, and we see that the collection of all the vectors in this direction t comma t is all going to be eigenvector for this or the invariant direction corresponding to this transformation T. So, the basically which is again going to be a subspace, this means this is a subspace, and this is also a subspace. These subspaces wherein which the effect of transformation is just to scale, these subspaces are called as invariant subspaces associated with a particular transformation. So, the invariant subspace of a linear map, say T, or let us say of a linear transformation T, from let us say a vector space V to another to the same vector space V. For example, T operating on vectors in Rn maps it to set of vectors in Rn. The invariant subspace of a linear transformation T from V to V is the set of vectors let us say u such that the transformation on the vector u is going to be lambda times u, where lambda is a scalar, lambda is a real scalar, we will say a scalar. These are called, this is basically the invariant subspace. So, in our example that we took for the matrix for T associated with the associated matrix, or for T which is going to map x y to 2x plus y and x plus 2y, the invariant subspaces are let us say 3 into we will put it as t comma t, we will take it as the set of all vectors t into 1 comma 1 t scalar and s into 1 minus 1 s real scalar. So, these are basically the invariant subspaces associated with the linear transformation T. Now, what are the applications of this invariant subspaces? Where do we go from here? So, do we have some interesting property associated with which arise out of this eigenvalues and eigenvectors? Can we do something interesting with A with employing these eigenvectors is something which we will see in the next class, where we are going to talk about diagonalization of the matrix A. So, in the next lecture that we are going to do, we will discuss diagonalization of A and matrix powers we will also see some small examples where we actually see our eigenvalues, eigenvectors, examples of let us say applications of eigenvalues and eigenvectors. And with that, this second module will get over, and we will start with third module after that with ideas of orthogonality. We will first define the idea of inner product, dot product, and then we will look at orthogonality, and if you have linearly independent vectors, how do we get orthogonal vectors from it, and real symmetric matrices and so on. So, that will be the focus of the next week's lecture, but we still have a small tail piece which is left over here, where we are going to look at diagonalization of matrix A and matrix powers, which we will actually see in the next lecture. Namaste.